Hello, everybody. So that video was not Shutterstock. That was actually Neuralink. So that's actual video from the company. So if you want to get a sense for what it's like to work at Neuralink, that video is indicative of the atmosphere of Neuralink. It's an incredibly talented team, and you're going to hear a lot from them tonight. So we're going to actually go quite into depth on what we're doing, why we're doing, how we're doing it, and I'm just incredibly impressed with the caliber of talent at Neuralink. And in fact, the main reason for doing this presentation is recruiting. And this will be a slow process where we will gradually increase the issues that we solve until ultimately we can do a full brain-machine interface. Yeah, this is going to sound pretty weird, but achieve a sort of symbiosis with artificial intelligence. But I think with a high bandwidth brain-machine interface, I think we can actually go along for the ride. And we can effectively have the option of merging with AI. I think this is extremely important.
Composed of nearly 100 billion cells called neurons. Neurons come in many complex shapes, but generally they have a dendritic arbor, a cell body called a soma, and an axon. The neurons of your brain connect to form a large network through axon-dendrite junctions called synapses. At these connection points, neurons communicate with each other using chemical signals called neurotransmitters. Neurotransmitters are released from the end of an axon in response to an electrical spike called an action potential. When a cell receives enough of the right kind of neurotransmitter input, a chain reaction is triggered that causes an action potential to fire, and the neuron to in turn relay messages to its own downstream synapses. Action potentials produce an electric field that spreads from the neuron and can be detected by placing electrodes nearby, allowing recording of the information represented by a neuron.
Our goal is to record from and stimulate spikes in neurons and do so in a way that is orders of magnitude more than anything that's been done to date, and safe and good enough that you can, it's not like a major operation. It's sort of equivalent to sort of a LASIK type of thing. So this is in contrast to the best FDA-approved system, which is like a Parkinson's deep brain stimulation thing, which would have on the order of 10 electrodes. So the system, even in version 1 that we're going to unveil today, is capable of 1,000 times more electrodes than the best system out there, and they're all read and write. So this is really quite, I think, I mean, for something to be 1,000 times more than what is publicly approved is quite a big difference. So there's very tiny threads that are about a tenth, roughly, of the cross-sectional area of a human hair. So they're extremely tiny threads. In fact, the threads that we have, like I said, even in version 1, are about the same size as a neuron. So if you're going to go stick something in your brain, you want it to not be giant, you want it to be tiny, and to be approximately on par with the things that are already there, the neurons. You really need this to be done with a robot because it's very tiny and it needs to be very precise. So you don't want to pierce a blood vessel. So when so each thread, the robot looks sort of basically through a microscope and inserts each electrode specifically, bypassing any vasculature, any kind of like blood vessel, and making sure that it can be inserted without causing trauma or minimal trauma. So just to give you a sense of scale, this is how tiny the threads are. That is not even a big finger, that is a small finger. So these threads are just like I said, way smaller than a hair, and there's 1,000 of them. And this is what the robot looks like. It's sort of quite a complex device, but it all comes down to a very tiny, tiny point. So we want to just like, you see the robot on the left, and then what looks like the needles for insertion next to a penny, but in fact the actual needle that gets inserted is way, way tinier. It's that little tiny thing at where the arrow is pointing. That's actually the size of the needle. It's about 24 microns in diameter. It's so small you can't really even see it in the picture with the penny. You can get a sense for the robot doing the electrode insertion. That's a very zoomed in view. So they're all very, very tiny, and the robot is very selectively applying them very delicately. And then this is what the chip looks like. So action potentials. So each one of those represents one electrode. So there would be up to 10,000 of these lines. The operation on a per chip basis, it involves just a 2 millimeter incision, which is dilated to 8 millimeters, and then the chip is placed through that, and then it goes back to being 2 millimeters, and you can basically glue it shut. You don't even need a stitch. And then the interface to the chip is wireless. So you have no wires poking out of your head. Very, very important. So it's basically Bluetooths to your phone. Because we'll have to watch the App Store updates for that one. Make sure we don't have a driver issue. And we hope to have this aspirationally in a human patient before the end of next year. So this is not far.
I'm Max Hodak. I'm the president of Neuralink. So I've wanted to build a neural interface has really been like a central goal of my life for basically as long as I can remember. I think like we talk about AI being potentially the last invention that we have. I think that a high bandwidth BMI might be like really the first invention in many ways of like the next chapter of us. It's just really like, as Elon alluded to earlier, everything about your experience, your thoughts, your memories, it's all in your brain and represented in the firing statistics of action potentials. We knew, as Elon mentioned, that whatever we built, we wanted it to be completely wireless. It had to be something that would last for a long period of time, not something that you'd have to take out at 2, 3, or 4 years in. This is a photo of some of the prototypes that we've gone through over that time. So we started on the far left. That's an entirely passive board that has 64 electrodes on it and connects to connectors that go to big external amplifiers. And then we added integrated electronics with our first custom chip. That's also 64 channels. And then there was a big leap to the device that Elon showed a photo of earlier. That has 3,072 electrodes in a fully implantable package with just a USB-C port coming out. And then we took a step back in channel count because remember we have to optimize safety, longevity, and bandwidth all together. And so in order to optimize some of those other things, we moved to an easier to manufacture system that has 1536 channels and a USB-C port. And those last two are the focus of the paper that we released today. And they taught us a lot about the architecture that we think was the basis for our first human product that we're calling N1. And the central component of that is the N1 sensor. It's a little hermetic package. When it's fully assembled, this is missing an outer mold. It's into an 8 millimeter diameter, 4 millimeter tall cylinder. Opening it up a little bit, you can see there's the thin film, which has the threads that Elon talked about, which is the wisp going off to the side. There's a hermetic substrate, and then that gets welded later to a package that goes over top, and that's mated to our custom electronics. And you really can't manipulate these with your hand. That part at the top is just a backing material that's surgical packaging. They're peeled off. The threads are peeled off that one at a time by the robot to place into the brain. And the first impetus for this is just you have to place these threads. You can't manipulate these threads. You need a robot. And then that grew into understanding where the blood vessels are and imaging into the tissue, and the surface of the brain moves because you're breathing and you have a heartbeat, and there's lots of complexity of dealing with this incredibly high entropy substrate. And so the N1 implant We can place, as Elon mentioned, many of these, possibly up to 10. In one hemisphere, for our first patients, we're looking at four sensors, 3 in motor areas and 1 in a somatosensory area. And that connects wirelessly through the skin to a wearable device that we call the Link, which contains a Bluetooth radio and a battery. It'll be controlled through an iPhone app. You won't have to go to a doctor's office and have them have an exotic programmer to configure it. And so for the first product, we're really focusing on 3 distinct types of control. The first is giving patients the ability to control their mobile device, because we heard from over and over again from patient groups that if you have to have a caretaker around to press buttons for you, what's the point? You might as well have them do the thing. You have to get self-sufficient using the devices on your own. But we are working as hard as we can towards our first in-human clinical study next year.
We developed this robot that can rapidly and precisely insert hundreds of individual threads representing thousands of distinct electrodes into the cortex in less than an hour. This tool allows a surgeon to aim between the blood vessels that cover the surface of the brain with micron-scale precision. Here, the robot is selecting individual electrode threads and placing them into the brain in the pre-planned location with remarkable accuracy and repeatability. When you think of traditional neurosurgery, you probably think of something very invasive. Traditional surgery on the brain isn't something that patients ever look forward to or are excited about, except in the most dire circumstances. Usually a clamp is attached to the skull to keep it rigidly immobilized to the operating table. We often shave all or most of the patient's hair. Patients can end up with large visible scars. At Neuralink, we want to create an entirely different patient experience, something more like LASIK. We even want this to be possible under conscious sedation. That means you can get rid of the complexity and the risk of general anesthesia, as well as many of the unpleasant side effects, nausea, sore throat from a breathing tube. But our aim is to simplify the procedure, down to the injection of local anesthetic, a very small opening in the skin, a painless opening in the skull below, quick and precise placement of threads into the cortex, and then we fill that hole in the skull with the sensor, allowing the scalp to be closed up over it.
Currently, there are no research or commercial devices that meet all of our requirements. So we built one out of microfabricated thin film polymers. And an average strand of hair is about 100 microns. Yet in this small footprint, we're able to fit our electrodes, our wires, and the insulation for each of those wires. This design is called Linear Edge. It's one of over 20 designs that we've made for our R&D work. We've progressively been increasing the number of electrodes per thread without significantly increasing the width of each of these threads at the base. Next, we assemble the electronics and then also attach a wired lid using a laser welding process. These 2 steps have required a lot of internal development as well. The result is the sensor that's ready for final assembly and implants into the body.
Since the start of Neuralink, we've gone through 3 major revisions to the analog pixel, progressively improving both the size and power while maintaining performance. And our latest pixel on the right is at least 5 times smaller than the known state-of-the-art of similar architecture with 1 pixel dedicated per electrode, as published in the academic literature. All of these functionalities that I outlined are integrated into a single 4x5 millimeter silicon die.
This is in fact traces of a bunch of electrodes that came off of one of our devices, a bunch of electrodes from a single thread. And each trace shows you the voltage waveform in time as it's coming off of one of those threads. We have algorithms that can detect these spikes in real time as they're happening. And that allows us to collect data that looks something like this. This is what we call a spike raster. So each row there represents 1 channel of recording, and time goes from left to right. And each of those little tick marks is the time of a single spike in action potential. Now, if you look at that, you might think that looks pretty messy and it's not clear what's going on. But I'm going to do a little trick. I'm going to take those neurons and I'm going to rearrange them so that they're in the order of the tuning that they have, just as I told you about those 2 neurons. And if you do that, look what happens. Now suddenly structure emerges. And I think you'll agree, looking at that that there's information in that stack of neurons that tells you about the movement. And that's exactly what we want to do. We want to do that kind of magic in an automated way to read out the movement. The way we do that is by building something that we call decoding algorithms. These are mathematical algorithms that we tune based on data like these to be able to take in just those rasters of spiking activity and output the movement that the person wants to make. For these little fake data, I built a very, very simple decoder, and sure enough, it's able to capture the intended movement. This is what we want to do on a bigger scale. That even if you're not actually making the movement, even if you're just thinking about the movement, or even if you're watching someone else make movement, the cells in motor cortex respond in a similar way. With that, we think that people will be able to get naturalistic control over the computers, not just a mouse, but also a keyboard, game controllers, and potentially other devices. That's what we're trying to do. So potentially, with a device like this, you could restore speech to a paralyzed person who's no longer able to talk. But there's no reason in principle that we can't reach all of motor cortex. And that would give us access to any movement that a person thinks about, any movement at all. A person could imagine running or dancing or even kung fu, and we would be able to decode that signal. What Neuralink wants to do is to give people the ability to tap into those representations, to get better access to that information, both to repair broken brain circuits and also to ultimately give us better access to better connections to the world, to each other, and to ourselves.